Hi, welcome to this presentation about the future of systems engineering practices that could happen or not. This presentation is just intended as a contribution to the analysis of changes that are required in engineering. It will try to identify some consequences on the practical digital resources that will be required for support and control of these engineering evolutions. It's presented here as a scenario of evolution in the fictional sector, which is inspired from a work of the System Engineering Research Center in 2009. And it's a kind of story of a fictional project led by Mary. Mary had slept poorly the last few nights. Her new product engineering management responsibility appeared increasingly overwhelming to her, and yet the initial definition of the product was already behind her. But the first feedback from the customers in operational use was not good, because the latest delivery went badly. It has to be said that everything was moving since the release of the product. Customers were requiring more and more complex functions. Changes and obsolescence constantly happened in the technologies used. New security and regulation constraints were issued every month. And of course, bugs were constantly reported, while users submitted change requests via the social and institutional network. This brought more and more constraints on time schedule to react faster, of course, under pressure of competitors. The evidence was indisputable. System engineering should extend to the whole life cycle of the product up to its retirement, and engineering was becoming an affair of evolving compromise, constantly called into question by its environment. Each time a new event happened impacting engineering, a new engineering increment had to be performed involving many stakeholders. Each event had consequences on the whole system, and this system engineering required confronting all stakeholder views so as to update the compromise in short loop in order to be reactive enough. But each stakeholder was working on their own scope, data, and concern, with few occasions to confront visions. For Mary and her team, harmonizing several concurrent engineering activities that way in agile and incremental mode turned out to be impossible without new capacities and tools. So taking benefit from the digital transformation applied to engineering, tools were defined for impact analysis and consistency control, addressing all the data and stakeholders concerned. This way, each major engineering concern and decision was analyzed, confronted with all the consequences for each party, and this allowed efficient arbitration between stakeholders. These tools were designed to be applicable to most engineering data, no matter the offering tools. Of course, requirements, solution architecture, interfaces, non-functional issues, design development, and production, assets, means, and so on. But also possibly apply to plan and effective processes, decisions, stakeholders' activities, actions, transformation and use of data, etc. So you have to remember that in this presentation, all those data have to be considered. You will see a car in this presentation as an example, an illustration of the processes, but in this presentation, in the same way as for Margaret, a pipe is not a pipe. In this presentation, a car is not a car, but it will represent any set of data or activities as well, of course. Well, Mary was now sleeping better, but for a shorter time. The conventional hierarchical way of working by delegation was turning out to be too slow, as it placed the activities in series. System engineering team used to delegate to subsystems, each of which would in turn delegate down to development disciplines. Contracts flew downwards, And once all levels would have completed development, integration, verification, and validation would flow upwards, and this was not very effective because it hindered the search for a global compromise and optimum engineering-wide. The continuous co-engineering approach had to be pushed still further in several ways. Teams members didn't want to work hierarchically anymore, but based on some key engineering issues or concerns. For example, addressing a new function or a new customer-required capability and trying to implement it, addressing performance or cybersecurity issues at all engineering levels together, of course, or solve a problem or fix a bug, etc. Each team was multidisciplinary and worked at several levels of engineering and development all together. In order to preserve coherency between these engineering teams and issues, a cross-functional analysis of the data enabling continuous short-loop adjustments between the stakeholders was implemented. This allowed monitored and controlled parallel working, along with the ability to analyze consequences of each choice on the whole system definition. Parallelization and concern-based co-engineering proved very effective for the definition and design phase, and that was the first great change in maritime. However, the IVV was not as much agile. There was still the black spot of the slow verification of each increment, and they started with the design and implementation of simulation and development as well, then of enabling systems and test environments, which did not benefit from the same agility properties, and up to sprint outputs, pre-production mockups, and production mean. Furthermore, consistency was maintained mainly manually between all these related assets. So, first, the team ensured the initialization, continuity, and consistency of simulation models, test campaigns and scenarios, test facilities, etc., down to production based on mechanized transformation of definition and design models. This speeded up the time to get appropriate simulation and test environments and allowed IVV to reach the same pace as definition increment. Well, of course, none of this would have been possible without the assisted capacity to maintain consistency between all these engineering assets and activities. Next innovation introduced by Maritime was to continuously analyze the activity of the engineering stakeholders, providing warnings and recommendations on them. Here came what the team called digital assistant. This contribution was based on analyzing engineering data, analyzing their transformations, and also actions performed on data and the use made of them by all stakeholders. This both helped to maintain the consistency of the data produced and predict the risk of divergence. This was a considerable leap, quantitative and qualitative, because freed from the tedious monitoring and management tasks, everyone now concentrated mainly on the activity creating added value, the choices and decisions, design, and the resolution of sticking points, etc., expecting automation for the rest. Of course, this significantly increased reactiveness and velocity of engineering, especially of increment. So, next enabler to success was the introduction of powerful software tools, robotizing or assisting the activities with low added value, such as massive simulation and test run, bridge with production and deployment, coherency control, engineering data traceability, updating and verification operations, etc. When it came to launching a much more ambitious product policy, there was nevertheless no lack of difficulties. The construction of the product lines of each stakeholder and each customer configuration was increasingly complex. The scope of the product line encompassed most data of engineering, of simulation, of development, but also production items and even operation information data and configurations, and all this in a joint manner. Each of these had different and dedicated assembly rules, and ensuring consistency of all these partial views of the product line approach was no mean feat. By chance, most required tools and resources were already in place, as seen previously. Robotization of the transformation between data of different stakeholders and specialties, mechanization of tedious tasks, including massive testing, maintenance of consistency, impact analysis, extension of the engineering to the entire scope of the company concerned, quality and efficiency control. Well, it was nevertheless necessary to add the capacities of assembling by complex rules and of joint product changes, also robotized, of course. This ended up enabling reactive engineering up to scale of product line. Last but not least point, by mutual agreement, the whole team chose freedom and personalization as sources of productivity in their day-to-day work. In short, everyone focused on their own needs, on their own views, and had the latitude to optimize their day-to-day work and tools. Complexity was hidden and managed thanks to mechanization and intelligence assistance. Consistency checking and management was now ensured through usage and data monitoring, which also allowed tight global control and alignment. Finally, of all those transformations, what Mary was proudest of was that each morning, all members of her team were now happy to come to work and proud of their work. And Mary suddenly realized how much her nights had become peaceful. This is the end of Mary's story. Just to summarize it, what we have seen is that management of complexity of engineering, which will increase, will evolve continuous and dynamic co-engineering between all the stakeholders in the development of small and short increments, but this will be made possible only if we have some powerful tools for automation, confrontation, and consistency of engineering data of each stakeholders. To finish, a quick view on consequences on the engineering tools of the future. So no prediction, no forecast, no pretension to precision, but just what kinds of new capabilities might be expected in order to support this kind of evolution in the state of the art in engineering tooling and support. The first thing is that one of the first consequences is that each engineering decision will necessitate bringing together data of all types, no matter the authoring tools, for example, within what we call a scope. This scope would group data independently of their source or independently of their level, system, subsystem, disciplines, specialties, and so on, and independently from the authoring tools that produce this data. The notion of scope introduced above is a central element of co-engineering and collaboration. Each group of stakeholders will define one or more scopes to manage their point of view, capitalizing its own data, constraints, rules, and analysis results, which identify its contribution in the overall compromise. Each engineering concern will bring together and confront those point of view and contributions in one or more scopes to analyze, compare, and if pertinent, reconcile with the different and previous one. Note that scope can overlap as those three engineering threads that have to work together. And they work possibly partly on the same kinds of data, which means in many cases, this will require the capacity to modify the same set of data concurrently in several scopes in order to address several concerns in parallel. A scope contents can be built from any engineering data and beyond to any company data. As you can see, we have to deal with all those engineering data and more, dealing with needs, solution architecture description, simulation, IVV, both on test results, patterns, and so on, but also specialties, engineering, safety, securities, and more, production assets, and of course, all that deals with operations monitoring through AMS, digital twins, IoT, and more. And this has to be applied to different engineering levels, from system up to development and production disciplines. And this has to be considered in a multi-project purpose, in a domain or in a product line as well. And this is even more complex because this is a simplistic representation, but the reality of each of these slices should be this one, which takes into account the fact that we have a decomposition tree that increases the number of data according to the different subsystems and parts and disciplines and components to be built at each level. This is extremely complex, and this is leading a huge problem in terms of complexity management because all those data have to evolve, and to evolve during time, not from a top-down manner, but has to be preserved in terms of consistency and coherency with each other. And this is problematic because we have, for this purpose, to maintain traceability, justification, relation links between all those data. And for the moment, those links may reach tens of thousands of numbers to be built and checked manually today, and this is probably not likely to support scalability to future level of complexity of our systems. This is clearly a big challenge, and if we succeed in solving it, it will not only be a digital transformation, but probably a digital revolution. As indicated above, the spirit of this vision is to avoid imposing a single vision on all engineering players at all times. But of course, this doesn't mean, however, that we should not exploit the opportunities in which the very construction of engineering data implicitly assumes coherence by construction. This is the case, for example, with the transformation of models, as presented here, for example, between architecture, simulation, development, test, production, deployment, and operation models. All those are related to each other. They share some elements. They have to be initialized and built according to each other. And usually they may also benefit from transformation from each of them. All those transformations having to be bidirectional, iterative, and conservative, of course. And hopefully they shall be mechanized so as to reach a truly scalable engineering. For these reasons, and in order to manage complexity, general purpose tools will be needed so as to ensure either a priori consistency through model transformation, notably what we have seen in the previous slide, or a posteriori reconciliation of models that may have evolved separately according to different parallel concerns and contexts. Just to finish this quick scope of advanced tooling capabilities, so what we have to deal with will be to be able to introduce explicit semantics and meaning on the data that we manage so as to be able to efficiently confront them to each other. We will have to get means to analyze data usage, engineering activities to guide and assist reconciliation and coherency maintenance as well. And of course, this will be ruled by real-time intelligence supervision of engineering tasks, the kind of technical governance of engineering that will have to deal with what we have seen previously. So formalization and monitoring of engineering processes, continuing monitoring of engineering data, status and changes, analysis of the activity of the stakeholders, detection, prediction, and resolution of divergences between all of them, and maintenance, of course, of an evolutive view at completion of the solution, including an encompassing global architecture vision, of course, that will evolve according to requirements, constraints, and results. But we will need this view at completion and a master plan, here again, that may and will probably have to evolve during time, but that will be a guarantee of global currency and ability to reach the engineering goals and the customer needs as well. This closes this presentation. I hope you enjoyed it. Thanks a lot. Bye bye.